Question 131. Your company wants you to build a highly reliable web application with a few public APIs as the backend. You don't expect a lot of user traffic, but traffic could spike occasionally. You want to leverage cloud load balancing, and the solution must be cost-effective for users. What should you do? A. Store static content such as HTML and images in Cloud CDN. Host the APIs on App Engine and store the user data in Cloud SQL. B. Store static content such as HTML and images in a cloud storage bucket. Host the APIs on a zonal Google Kubernetes Engine cluster with worker nodes in multiple zones, and save the user data in Cloud Spanner. C. Store static content such as HTML and images in Cloud CDN. Use Cloud Run to host the APIs and save the user data in Cloud SQL. D. Store static content such as HTML and images in a cloud storage bucket. Use Cloud Functions to host the APIs and save the user data in Firestore. Upon reassessing the question and options, option C still remains the most correct choice. Explanation for the selection of option C. 1. Cloud load balancing and cost effectiveness. Cloud load balancing provides global distribution and scalability of web traffic. The combination of Cloud CDN and Cloud Run ensures that the backend scales as required without the need for manual intervention. Cloud Run automatically scales based on incoming traffic, which is perfect for handling spikes in traffic while remaining cost-effective, as you only pay for the compute time used. 2. Cloud CDN for static content. Cloud CDN is used to cache static content, like images, CSS, HTML, at the edge, reducing latency and offloading the origin servers. This setup reduces server load and improves application performance. 3. Cloud Run for APIs. Cloud Run is ideal for stateless applications, as it scales automatically based on traffic. It's easy to deploy, cost-effective, and well-suited for small to medium traffic web applications with occasional spikes. It's much more lightweight and manageable compared to setting up a Kubernetes cluster, which can be complex and require more management effort. 4. Cloud SQL for user data. Cloud SQL offers managed relational databases that are easy to use, cost-effective, and scalable. It's perfect for storing structured user data in this scenario. Why the other options are less ideal? Option A. Hosting the APIs on App Engine can be a good option, but it's not as cost-effective or flexible as Cloud Run, especially for applications with low to moderate traffic. App Engine's pricing structure can become less economical as traffic patterns fluctuate. Cloud SQL for user data is fine, but Cloud Run provides better cost control and scalability for handling APIs. Option B. GKE with worker nodes in multiple zones introduces unnecessary complexity for a small-scale application that doesn't require complex Kubernetes orchestration. This also results in higher operational overhead. Cloud Spanner is a powerful, globally distributed relational database, but it's often an overkill for small applications with moderate traffic and would likely be more expensive than Cloud SQL. Option D. While Cloud Functions is a good choice for lightweight, event-driven workloads, it's not as suitable for managing APIs with the kind of backend persistence and user data management required for this scenario. Firestore is a NoSQL database and would be more suitable for applications requiring flexible document storage, not for traditional relational user data. Conclusion. Option C remains the best choice because it combines scalability, cost efficiency, and ease of management using Cloud Run for APIs, Cloud CDN for static content, and Cloud SQL for user data storage. This solution is the most streamlined and cost-effective for a web service that doesn't expect constant traffic but needs to handle occasional spikes. Question 132. Your company sends all Google Cloud logs to cloud logging. Your security team wants to monitor the logs. You want to ensure that the security team can react quickly if an anomaly such as an unwanted firewall change or server breach is detected. You want to follow Google recommended practices. What should you do? A. Schedule a cron job with Cloud Scheduler. The scheduled job queries the logs every minute for the relevant events. B. Export logs to BigQuery, and trigger a query in BigQuery to process the log data for the relevant events. C. Export logs to a pub subtopic, and trigger cloud function with the relevant log events. D. Export logs to a cloud storage bucket, and trigger cloud run with the relevant log events. The best approach in this scenario would be option C. Export logs to a pub subtopic, and trigger a cloud function with the relevant log events. Explanation. Exporting logs to Cloud Pub Sub is a highly scalable, real-time messaging service that can handle high volumes of log data from cloud logging. When you export logs to a pub subtopic, you can easily capture log data as it is generated and then process it in real time. Triggering a cloud function with the relevant log events enables immediate processing and response to any anomalies or security events. Cloud functions are serverless, event-driven compute services that allow you to process logs in real time without managing servers. This fits well with the need for quick detection and response to potential security issues, such as unwanted firewall changes or server breaches. This approach aligns with Google's best practices for handling large-scale log management and alerting systems. Google recommends using PubSub for real-time event-driven processing of logs, making this a highly effective solution for the security team's requirements. Why other options are less suitable? Option A. Schedule a cron job with Cloud Scheduler introduces delays because it involves polling the logs periodically. By the time an anomaly is detected, the security team may not be able to react quickly enough. It is not ideal for real-time log monitoring and response. Option B. Export logs to BigQuery and trigger a query is not the best tool for real-time event processing. While BigQuery is excellent for data analysis, it may introduce delays when querying logs, and querying logs every minute might not be quick enough for urgent security needs. Option D. Export logs to cloud storage and trigger cloud run is designed for storing large amounts of unstructured data, not for real-time log processing. Triggering a Cloud Run service from cloud storage could introduce latency, and Cloud Run is better suited for serving applications rather than processing logs. Conclusion. Option C is the best choice because it uses PubSub and cloud functions to provide real-time log monitoring and instant responses. This approach allows the security team to act quickly upon detecting anomalies and follows Google's best practices for handling log data at scale and in real time. Question 133. You have deployed several instances on Compute Engine. As a security requirement, instances cannot have a public IP address. There is no VPN connection between Google Cloud and your office, and you need to connect via SSH into a specific machine without violating the security requirements. What should you do? A. Configure CloudNAT on the subnet where the instance is hosted. Create an SSH connection to the CloudNAT IP address to reach the instance. B. Add all instances to an unmanaged instance group. Configure TCP proxy load balancing with the instance group as a backend. Connect the instance using the TCP proxy IP. C. Configure identity-aware proxy (IAP) for the instance and ensure that you have the role of IAP-secured tunnel user. Use the gcloud command line tool to SSH into the instance. D. Create a bastion host in the network to SSH into the bastion host from your office location. From the bastion host, SSH into the desired instance. The best approach in this scenario is option C. Configure identity-aware proxy (IAP) for the instance and ensure that you have the role of IAP-secured tunnel user. Use the gcloud command line tool to SSH into the instance. Explanation. With identity-aware proxy (IAP), you can securely connect to instances without the need for public IP addresses or a VPN. IAP allows SSH access to Compute Engine instances that do not have public IPs, using a secure tunnel through Google's infrastructure. This method ensures that access is controlled by IAM roles, providing strong authentication and security. By ensuring that you have the IAP-secured tunnel user role, you can authenticate and SSH into the machine via gcloud without violating the requirement of not using public IPs. Why other options are less suitable? Option A. Configure CloudNAT on the subnet where the instance is hosted. Create an SSH connection to the CloudNAT IP address to reach the instance. CloudNAT provides outbound internet access for instances without public IPs but does not support inbound SSH connections directly. It's mainly used for enabling instances without public IPs to access external resources, not for SSH access to those instances. Option B. Add all instances to an unmanaged instance group. Configure TCP proxy load balancing with the instance group as a backend. Connect the instance using the TCP proxy IP. While TCP proxy load balancing can be used to route traffic to instances, it's typically intended for web applications and load balancing, not specifically for SSH connections. It also adds unnecessary complexity when IAP provides a more straightforward and secure way to achieve the same goal. Option D. Create a bastion host in the network to SSH into the bastion host from your office location. From the bastion host, SSH into the desired instance. Setting up a bastion host introduces additional infrastructure management and potential security risks. While it can be an effective solution, it's less efficient and requires maintaining a separate instance to facilitate SSH access, whereas IAP provides a simpler, managed alternative without needing an additional bastion host. Conclusion. Option C is the best choice as it uses identity-aware proxy, IAP, to securely SSH into instances without public IPs, aligning with Google's security best practices. This approach eliminates the need for complex networking configurations or additional infrastructure while maintaining security and ease of use. Question 134. Your company is using Google Cloud. You have two folders under the organization, finance and shopping. The members of the development team are in a Google group. The development team group has been assigned the project owner role on the organization. You want to prevent the development team from creating resources in projects in the finance folder. What should you do? A. Assign the development team group the project viewer role on the finance folder, and assign the development team group the project owner role on the shopping folder. B. Assign the development team group only the project viewer role on the finance folder. C. Assign the development team group the project owner role on the shopping folder, and remove the development team group project owner role from the organization. D. Assign the development team group only the project owner role on the shopping folder. The most appropriate choice is option C. Assign the development team group the project owner role on the shopping folder, and remove the development team group project owner role from the organization. Explanation. In Google Cloud, IAM roles are inherited through the hierarchy of your organization, folders, and projects. By default, roles assigned at the organization level propagate down to all resources within the organization, including folders and projects. To limit the development team's ability to create resources in specific folders, you need to 1. Remove the project owner role from the organization to prevent the development team from creating resources in the finance folder or any other projects in the organization that they should not manage. 2. Assign the project owner role only on the shopping folder to ensure that they have sufficient permissions to manage resources only in the shopping folder and not in finance. This solution aligns with the principle of least privilege and ensures that the development team has appropriate access to the shopping folder but is restricted from modifying or creating resources in the finance folder. Why other options are less suitable? Option A. Assign the development team group the project viewer role on the finance folder, and assign the development team group the project owner role on the shopping folder. This approach would only restrict the development team from creating resources in the finance folder but still allows them to perform all project owner activities in the organization. Since the role assigned at the organization level overrides folder-level assignments, they would still retain full control over all projects in the organization unless the role is explicitly removed from the organization. Option B. Assign the development team group only the project viewer role on the finance folder. This option only limits the development team's ability to create resources in the finance folder, but it does not prevent them from being able to create resources in other projects or folders under the organization. The development team would still retain project owner access at the organization level, making this an incomplete solution. Option D. Assign the development team group only the project owner role on the shopping folder. While this would restrict the development team to managing resources only within the shopping folder, it leaves the project owner role intact at the organization level, giving them the ability to create resources in the finance folder as well. This does not fully restrict them from creating resources in finance, making it an insufficient solution. Conclusion. Option C is the best approach as it ensures the development team is restricted from creating resources in the finance folder and can only manage resources in the shopping folder. By removing the project owner role at the organization level, this provides the necessary access control in alignment with the principle of least privilege. Question 135. You are developing your microservices application on Google Kubernetes Engine. During testing, you want to validate the behavior of your application in case a specific microservice should suddenly crash. What should you do? A. Add a taint to one of the nodes of the Kubernetes cluster. For the specific microservice, configure a pod anti-affinity label that has the name of the tainted node as a value. B. Use Istio's fault injection on the particular microservice whose faulty behavior you want to simulate. C. Destroy one of the nodes of the Kubernetes cluster to observe the behavior. D. Configure Istio's traffic management features to steer the traffic away from a crashing microservice. The most appropriate choice is option B. Use Istio's fault injection on the particular microservice whose faulty behavior you want to simulate. Explanation. Istio's fault injection feature allows you to simulate various failure scenarios within your microservices architecture, such as delays, errors, or service crashes. This is a built-in capability that helps you test how the system behaves under failure conditions without needing to modify the application code or infrastructure manually. In your case, using fault injection to simulate the crash of a specific microservice will give you the desired outcome of validating the behavior of the application in the event of such failures. Why other options are less suitable? Option A. Add a taint to one of the nodes of the Kubernetes cluster. For the specific microservice, configure a pod anti-affinity label that has the name of the tainted node as a value. This option involves a complex setup and is not specifically designed to simulate failures or crashes of individual microservices. A taint is generally used to control which workloads should or should not be scheduled on specific nodes, and using it in this context might not effectively simulate the desired fault condition for testing application behavior. It is more of a scheduling mechanism, not a fault simulation tool. Option C. Destroy one of the nodes of the Kubernetes cluster to observe the behavior. While destroying a node could lead to a failure scenario, this is an extreme and impractical approach for testing purposes. It can cause unnecessary disruption to other parts of the application and is not a controlled or efficient method to simulate failures of individual microservices. Option D. Configure Istio's traffic management features to steer the traffic away from a crashing microservice. This option might help in mitigating the effects of a crash but does not simulate the crash itself. While Istio's traffic management can reroute traffic, it does not allow for the controlled simulation of a fault or failure in a microservice. It's better used in conjunction with fault injection but does not replace it for failure testing. Conclusion. Option B is the best approach for simulating a failure in a microservice within a Kubernetes environment using Istio's fault injection feature. This solution provides a controlled and efficient way to validate how your application handles failures and recoveries, aligning with best practices for testing microservices resilience. Question 136. Your company is developing a new application that will allow globally distributed users to upload pictures and share them with other selected users. The application will support millions of concurrent users. You want to allow developers to focus on just building code without having to create and maintain the underlying infrastructure. Which service should you use to deploy the application? A. App Engine. B. Cloud Endpoints. C. Compute Engine. D. Google Kubernetes Engine. The best option for deploying this globally distributed application with minimal infrastructure management is option A. App Engine. Explanation. App Engine is a fully managed serverless platform provided by Google Cloud. It allows developers to focus purely on writing and deploying code without worrying about managing the underlying infrastructure. It automatically scales based on traffic, making it ideal for applications that support millions of concurrent users. App Engine abstracts away the complexities of managing servers, networking, and scaling, ensuring high availability and performance for globally distributed applications. Why other options are less suitable? Option B. Cloud Endpoints. Cloud Endpoints is a service for managing APIs, but it is not a platform for hosting or deploying entire applications. It helps you expose APIs but does not handle the deployment or scaling of the application itself. While Cloud Endpoints can complement an App Engine or other application deployment, it is not suitable as the primary service for deploying the full application. Option C. Compute Engine. Compute Engine provides virtual machines, VMs, that offer more control over the infrastructure. While this gives flexibility in terms of customization, it requires more management effort for scaling, patching, and maintaining the infrastructure. For a globally distributed application with millions of users, managing VMs manually can be complex and time-consuming, making it a less efficient choice compared to App Engine, which abstracts away much of that complexity. Option D. Google Kubernetes Engine, GK. GK is a powerful platform for running containerized applications with Kubernetes. While it is highly flexible and scalable, it requires more management effort compared to App Engine. You would need to manage container orchestration, scaling policies, and cluster configurations. While GKE is excellent for containerized applications with specific infrastructure requirements, App Engine offers a simpler solution for developers who want to focus solely on application code without managing the underlying infrastructure. Conclusion. Option A. App Engine is the best choice for deploying a globally distributed application with millions of users, as it fully manages the infrastructure and allows developers to focus on coding without worrying about scaling or maintaining servers. Question 137. Your company provides a recommendation engine for retail customers. You are providing retail customers with an API where they can submit a user ID and the API returns a list of recommendations for that user. You are responsible for the API lifecycle and want to ensure stability for your customers in case the API makes backward incompatible changes. You want to follow Google recommended practices. What should you do? A. Create a distribution list of all customers to inform them of an upcoming backward incompatible change at least 1 month before replacing the old API with the new API. B. Create an automated process to generate API documentation and update the public API documentation as part of the CI/CD process when deploying an update to the API. C. Use a versioning strategy for the APIs that increases the version number on every backward incompatible change. D. Use a versioning strategy for the APIs that adds the suffix €deprecated to the current API version number on every backward incompatible change. Use the current version number for the new API. The best option is option C. Use a versioning strategy for the APIs that increases the version number on every backward incompatible change. Explanation. Using a versioning strategy that increases the version number on every backward incompatible change is a Google recommended practice for maintaining API stability and supporting backward compatibility. This approach clearly communicates to consumers of the API which version they are using and ensures that they can continue using older versions until they are ready to upgrade to a new version. It also allows the API to evolve over time without breaking existing integrations. Why other options are less suitable? Option A. Create a distribution list of all customers to inform them of an upcoming backward incompatible change at least 1 month before replacing the old API with the new API. While notifying customers about changes is important, it does not provide a robust strategy for handling backward incompatible changes. Simply informing customers about the change does not allow for the safe and structured evolution of the API. Versioning the API provides a more reliable and standardized approach for both the developers and customers. Option B. Create an automated process to generate API documentation and update the public API documentation as part of the CI/CD process when deploying an update to the API. Updating the API documentation automatically as part of CI/CD is a good practice for ensuring that documentation is always up to date. However, this alone does not address the core issue of ensuring stability during backward incompatible changes. Without a proper versioning strategy, customers may still face disruptions when changes occur. Option D. Use a versioning strategy for the APIs that adds the suffix deprecated to the current API version number on every backward incompatible change. Use the current version number for the new API. While marking old versions as deprecated can be useful, it does not provide a clear, structured method for managing backward incompatible changes. Simply adding deprecated to the version number does not help with handling changes in a predictable and systematic way. It is more important to increase the version number itself to signal new major versions with backward incompatible changes. Conclusion. Option C. Use a versioning strategy for the APIs that increases the version number on every backward incompatible change is the most robust and reliable solution, as it allows the API to evolve while maintaining stability for existing users. It is a widely recommended approach for managing APIs over time. Question 138. Your company has developed a monolithic, three-tier application to allow external users to upload and share files. The solution cannot be easily enhanced and lacks reliability. The development team would like to re-architect the application to adopt microservices and a fully managed service approach, but they need to convince their leadership that the effort is worthwhile. Which advantages should they highlight to leadership? The new approach will be significantly less costly, make it easier to manage the underlying infrastructure, and automatically manage the CI/CD pipelines. B. The monolithic solution can be converted to a container with Docker. The generated container can then be deployed into a Kubernetes cluster. C. The new approach will make it easier to decouple infrastructure from application, develop and release new features, manage the underlying infrastructure, manage CI/CD pipelines and perform A/B testing, and scale the solution if necessary. D. The process can be automated with Migrate for Compute Engine. The best option is option C. The new approach will make it easier to decouple infrastructure from the application, develop and release new features, manage the underlying infrastructure, manage CI/CD pipelines and perform A/B testing, and scale the solution if necessary. Explanation. Re-architecting a monolithic application into microservices brings several advantages that are essential for modern cloud-native applications. These advantages include decoupling infrastructure from the application, which allows each service to be independently managed and scaled, making it easier to separate concerns and improve flexibility. It also enables developing and releasing new features because teams can work on individual services without affecting the entire application, allowing faster and more frequent releases. Managing the infrastructure becomes simpler with fully managed services like Kubernetes or Cloud Run, which reduce operational complexity. Microservices architecture is well suited for continuous integration and delivery, CI/CD, as each service can be developed, tested, and deployed independently. It also makes A/B testing easier by deploying multiple versions of a service and directing traffic accordingly. Furthermore, microservices allow horizontal scaling, where individual services can scale independently based on demand. These advantages are central to modernizing an application and are key reasons why organizations transition from monolithic to microservices-based architectures. Why other options are less suitable? Option A mentions cost savings and automatic CI/CD management, but it oversimplifies the potential advantages of microservices. Cost savings and automatic management are not guaranteed and depend on various factors, such as system complexity, existing infrastructure, and resources required for the transition. The broader set of benefits, including flexibility in scaling and decoupling, is missing. Option B focuses on containerization but does not address the core benefits of adopting microservices. While containerizing the monolithic app is a first step, it does not provide the same flexibility, scalability, and maintainability that microservices architecture offers. Option D suggests using Migrate for Compute Engine, a tool for lifting and shifting virtual machines to Google Cloud, but it does not help with re-architecting a monolithic app into microservices. The question focuses on re-architecting the solution, and Migrate for Compute Engine does not provide the necessary architectural benefits of microservices. Conclusion. Option C is the most comprehensive and accurate explanation of the advantages of adopting a microservices architecture with fully managed services. It highlights the key benefits of flexibility, scalability, development speed, and operational efficiency that would be most valuable to leadership when considering a move to microservices. Question 139. Your team is developing a web application that will be deployed on Google Kubernetes Engine, GK. Your CTO expects a successful launch, and you need to ensure your application can handle the expected load of tens of thousands of users. You want to test the current deployment to ensure the latency of your application stays below a certain threshold. What should you do? A. Use a load testing tool to simulate the expected number of concurrent users and total requests to your application, and inspect the results. B. Enable autoscaling on the GKE cluster and enable horizontal pod autoscaling on your application deployments. Send curl requests to your application, and validate if the autoscaling works. C. Replicate the application over multiple GKE clusters in every Google Cloud region. Configure a global HTTP/S load balancer to expose the different clusters over a single global IP address. D. Use Cloud Debugger in the development environment to understand the latency between the different microservices. The best approach is option A. Use a load testing tool to simulate the expected number of concurrent users and total requests to your application, and inspect the results. Explanation. Before a production launch, testing the application's ability to handle expected traffic is critical to ensure it meets performance and reliability requirements. A load testing tool is designed to simulate the load of concurrent users and requests on your system, giving you a clear picture of how your application performs under stress. You can measure various metrics such as latency, error rates, and response times during the test. By using such a tool, you can identify bottlenecks, optimize performance, and ensure your application meets the latency thresholds before deployment. Why other options are less suitable? Option B suggests enabling autoscaling and sending requests using curl to validate it. While autoscaling is important for handling increased traffic, testing with curl does not simulate realistic user behavior or the scale of traffic you expect. It also won't effectively test the application under load, which is essential for identifying potential performance issues. Option C involves replicating the application across multiple clusters and configuring a global HTTP/S load balancer. While this setup may help with high availability and global traffic distribution, it is not specifically related to testing the application's ability to handle load. Load balancing and cluster replication do not provide insights into performance under stress. Option D suggests using Cloud Debugger, which is useful for debugging issues in development environments but is not a tool for testing latency under load. It does not simulate high traffic or help evaluate whether the application can handle tens of thousands of users. Conclusion. Option A is the best choice as it focuses directly on load testing, which is necessary to ensure the application can handle the expected load and maintain latency thresholds. This will provide valuable insights into the application's performance before launching it to production. Question 140. Your company has a Kubernetes application that pulls messages from PubSub and stores them in file store. Because the application is simple, it was deployed as a single pod. The infrastructure team has analyzed PubSub metrics and discovered that the application cannot process the messages in real time. Most of them wait for minutes before being processed. You need to scale the elaboration process that is I/O intensive. What should you do? A. Use kubectl autoscale deployment app_name max 6min to CPU%50 to configure Kubernetes autoscaling deployment. B. Configure a Kubernetes autoscaling deployment based on the subscription push_request_latencies metric. C. Use the enable autoscaling flag when you create the Kubernetes cluster. D. Configure a Kubernetes autoscaling deployment based on the subscription num_undelivered_messages metric. The best option is option D. Configure a Kubernetes autoscaling deployment based on the subscription num_undelivered_messages metric. Explanation. In this scenario, the issue is that the application cannot process messages in real time, leading to a backlog. The metric subscription num_undelivered_messages tracks the number of messages that haven't been processed yet, which indicates that the application is lagging behind in processing. By using this metric to configure autoscaling, Kubernetes can automatically adjust the number of pods based on the backlog of unprocessed messages. This ensures that the application scales appropriately when there is a high volume of messages, allowing it to process them in real time. Why other options are less suitable? Option A suggests autoscaling based on CPU usage, CPU %50. While CPU utilization can be a useful metric for scaling applications, the application in question is I/O-intensive, storing messages in file store, so CPU usage may not be the best indicator of when to scale. Additionally, this method doesn't directly address the backlog or lag in message processing. Option B suggests configuring autoscaling based on the subscription push_request_latencies metric. This metric measures the latency of incoming messages but doesn't necessarily indicate whether the application is processing messages efficiently. Focusing on message latency rather than the number of unprocessed messages may not directly resolve the backlog issue. Option C suggests using the enable autoscaling flag when creating the Kubernetes cluster. While this flag enables autoscaling for the cluster itself, it does not define the specific scaling criteria or metrics to use. It also doesn't address the need to scale based on the backlog of messages being processed. Conclusion. Option D is the best choice because it focuses on scaling the application based on the number of undelivered messages, which is the core issue in this case. By doing so, you ensure that your application scales in response to the actual processing backlog and can handle the load more effectively.